Okay, so looking at this one, which has to do with Snell's law, but don't let that confuse you. Basically, the light is traveling from P1 to this point, and then through, it gets refracted into the water. So the distance, let's call this T for a second. So if you think of the distance P to T, that distance would be, using Pythagoras in that top triangle in the air, would be the square root of a squared plus x squared. And then think of the distance from T to P, sorry, that's P2, that's P1. Again, using Pythagoras, you've got a b squared plus a c minus x squared. There. All right, so what we're interested in showing the light will travel, so it says shortest possible time. That's too many words for me, so I'm just picking out the important ones. Shortest possible time. Now remember, speed equals distance over time, so time is distance over speed. The speed for this part being v1 in the air, and the speed for this one being v2 in the water. So the part that's in the air, if I look at my total time, so the P1 to T is root a squared plus x squared. So that's the distance over the time being, as the speed being v1. And then I'm also going in the water part, so there's the water distance and the velocity, the speed is v2 for that part. All right, so that's our the total time it's going to take, and then we want to minimize it. We want the shortest possible time, so we know we're going to find t dash. All right, in order to find t dash, think of this as, let me just rewrite t to make it easier for you. So think of this as a squared plus x squared to the power of a half, and this one b squared plus c minus x squared to the power of a half of v2. So t dash. So a half, this half is going to come down to the front, so it's going to be 2v1. And then I'm still going to have a squared plus x squared, but it's now going to be, oops, to the minus half. Then I'm going to have to go inside and different. So it's chain rule, and I'll get a 2x for that part here. So put 2x there. So the 2's actually cancel. Yeah, so what I am getting is x on v1. Sorry, I'm doing it in tiny bits here. Square root of that on that. All right, so what about this part over here? So the v2 is here. This half will come down, so it is a 2v2. I'm still going to get this bracket, c minus x, is it squared? C minus x all squared, and I'm putting the square in the wrong spot. That should be out there. C minus x all squared, sorry about that. To the minus a half now, chain rule, so go inside here, and you'll get 2, lots of the bracket, to the power of 1, and then inside that is a -1, so I'll just change that to a negative. All right, so chain rule on a chain rule there. All right, so what does that give us? Well, those 2 cancel. So we're going to have a minus c minus x on a v2 on a square root of b squared plus c minus x all squared. All right, nice. Now remember, in order to minimize or find the shortest possible distance, sorry, this is shortest possible time, we're looking for where t dash equals 0. And if you look at this, so this is a hint here, but anyway, so if I look at what sine theta 1 is from this triangle, some old tags, so I'm going to get x over the square root of our a squared plus x squared is going to be my sine theta 1. Oh, look at that. That's what I've got there. So this is the same as going sine theta 1 on v1, and in the exact same way sine theta 2, using our triangle in the water, some old tag, so the opposite is c minus x, and then the hypotenuse is the the b squared plus c minus x squared part. All right, which is all of this. So you can see this is going to be minus sine theta 2 on v2. Now for t dash to equal 0, you can see that means sine theta 1 on v1 has to equal sine theta 2 on v2. If I just, because that was a minus, I'm just putting it on the other side of my equal sign. All right, which gives us that bit there. So yes, in order to minimize this, sine theta 1 on v1 has to equal sine theta 2 on v2. Where the light, yeah, so I think that's all you have to show. We could do also double dash and just show it's a minimum. Yeah, so if we did double dash, looking at my dashes, which are really, where am I looking? I think I'm looking here. I'll probably get this wrong. Oh yeah, I can't be bothered. So I doubt you have to go that far actually for this one. It's just trying to get you to think about using geometry with your, we're not solving any further, just geometry, light refraction, so using trigonometry to help us solve this find a condition for it. Yeah, okay.